Hello. This is a video on finding formulas for sequences. We're going to be thinking about sequences and functions. A sequence is a special type of function in which the inputs are the natural numbers. Let's take a look at some example functions on Desmos. Okay, here's a linear function y equals mx plus b. By the way, if you're unfamiliar with functions, you might want to look at a little bit more basic video. I'm going to assume that you've at least seen functions a little bit before. Y equals mx plus b. M is 2 in this case, and b is 3. M is the slope. So here's a slope of 2. Here's a slope of 1/2. Here's a slope of 1, which means it's going to be on a 45-degree angle. We can have a negative slope, which means it's going to be going down and to the right. B is the starting value. It's this point here on the y-axis, which is 0, 3. Here, the y-intercept is 0, 4. If b is 0, we have a special type of linear function, which we're going to call direct variation. In this particular case, y equals 1.5x. This means that x and y are proportional. Now let's look at a quadratic. So h of x equals a times x squared plus b times x plus c. And I do want sliders for all three. So a is going to affect the curvature, and if a is negative, the quadratic function is going to go down. The c value is going to affect the y-intercept. So here we can see that we have 1x squared plus 1x plus 3.5. C is 3.5, and that is the y-intercept. I want to show you how to make a table here. To make a table in Desmos, you hit the plus, which allows you to add these things. I'm going to add a table. And here are the x values. Typically for a sequence, we'd want 1, 2, 3, 4, 5, for example. And then over here, we can tell what we want. We want h of x1, h of, and to get a subscript, you just hit the 1 like that. And so now we have these points graphed here, and they are blue. My original curve is red, and my blue points are shown here. And if I change C to maybe positive 2, for example, I get these ordered pairs, 1, 4, 2, 8, and so on. Now I'd like to look at our handout. The 5 types of functions we're going to be working with are proportional, which is a direct variation. This is the special type of linear function where the y-intercept is 0. By the way, I should indicate what we mean by proportional. If we divide both sides of y equals kx by x, for example, we get y over x equals k, and k is the constant. X and y are variable, but k is constant. So if I have a couple of ordered pairs, y1 over x1 equals y2 over x2. And the proportional relationship, again, is a line that goes through the origin. If they're proportional, we're going to also have the ordered pair 0, 0. The linear function, which is the arithmetic, is y equals mx plus b. The quadratic is there. The cubic is third degree with 4 terms. And the exponential, or the geometric function, is y equals a times b to the x. Now, previous in the course, we've already worked with arithmetic and geometric sequences, and we had a recursive form and an explicit form. The slope-intercept form for the arithmetic is y equals mx plus b. This is a close relative here. My common difference, I use d. Now the common difference is m. M is the common difference. And b is kind of like a0. It's the point when n would be 0. In a similar manner, for geometric, we have our recursive formula, we have our explicit formula, and our exponential form will be y equals a times b to the x, where a is the starting value, the y-intercept, kind of like a naught, if you will. So, how are we going to do this? Well, what do the questions look like? The questions are going to look like this, where we have a sequence of numbers here, and we're trying to determine what type of function it is. So here's the secret. You look at the differences, which means we're going to subtract. If the first row of differences is constant, then the function is linear, first degree. If the second row of differences is constant, then the function is quadratic, and so on. This is a very powerful relationship and a very important secret. So you look at the differences, and I'm going to show you some examples. On the other hand, if the differences do not turn out to be constant, it's probably not a polynomial. So you look at the quotients. And if the first row of quotients is constant, then the function is exponential. So let's look at some examples. Well, I guess before we do the examples, we need to make this observation. We have a quadratic function here. Here's what would be when you plug in 1, a times 1 plus b times 1 plus c. Here's what we would get when we plug in n equals 2. Here's what we get for n equals 3 and n equals 4. Here's the first row of differences. 4a plus 2b plus c minus a plus b plus c gives me this. Here's the first row of differences. And if I subtract those differences, I get 2a. We're going to be using this fact later on. So let's take a look at some examples. Okay, example 1. Let me get my pen. I prefer to make a table, a good old-fashioned XY table, which we use over and over and over again, starting in 8th grade algebra, maybe even before, all the way through college. So I have 8.1, 11.1, 14.1, 17.1, and 20.1. If I look at my differences here, I'm getting a constant 3. This first row of differences is constant, which means it is going to be linear. It's going to be of the form y equals mx plus b. Not only that, but the common difference is the common difference, which is my slope. So we're going to have y equals 3x plus something. Then what we need to do is we need to recover the starting value for x equals 0. So let me make a little space for x equals 0. Well, the common difference is 3. I'm adding 3 coming down the list, which means I'd have to subtract 3 to get up here, which is 5.1. Now, you might want to check this with a graphing calculator or check it with Desmos. So my answer, A, linear. If you want to write arithmetic, that's fine. And answer B is y equals 3x plus 5.1. If you wish for part B, you can answer it this way. AN equals 3n plus 5.1. I hope you're seeing the connection between the three types of formulas. There are three ways to write the formula: the recursive form, the explicit form, and the slope-intercept form. Now let's go to example 2. I'm going to make my good old-fashioned formula, or good old-fashioned table. This time I'm going to leave room for the 0 point. So I have 3, 6, 9, 12. Actually, this one happens to have the same common difference. That's coincidence. And if we come back here to the 0 point, I'm getting 0. When I have a linear function that goes to the point 0, 0, this is direct variation. Which means it's proportional. And my formula is y equals 3x, or an equals 3n. Now let's go to our third example. Make our table. 1, 6.5, 2, 9, 3, 13.5, 4, 20, 5, 28.5. So I look at my differences. 2.5, 4.5. Now you want to make sure that you're subtracting the lower number minus the upper number. And you could get negatives. 20 minus 13.5 is 6.5. 28 minus 20 is 8.5. Subtract consistently. Now, if I do my second row of differences, I'm getting a constant of 2. When the second row of differences is constant, it's quadratic. Answer A is quadratic. Also, we saw up above that the second difference is 2a, which means that 2a equals 2. This implies that a equals 1. So for part B, I'm going to have y equals ax squared plus bx plus c. I know that a is 1. Now I'm going to recover the 0 point. The 0 point is going to tell me c. So we're going to have a difference here, which means we're going to have a difference here. This difference here is 2, which means I'm subtracting 2. Follow your pattern. So this is going to be 0.5. And if I subtract 0.5, that should take me to 6. So this value right here C equals 6 because it is the y-intercept. Now I only need to find B. And you can use any of the ordered pairs to find B. I think I'm going to use this ordered pair because it doesn't have any decimals in it. So plugging in for x and y, I have 9 equals 2 goes in for x, so that's going to be 4 plus 2b plus 6, which means 2b equals -1, which means b equals -0.5. So now I'm ready to write my equation. Y equals x squared minus 0.5x plus 6, or an equals n squared minus 0.5n plus 6. Now let's move to example 4. So we need to write down our table. Looking at our differences, we have a difference of 11, a difference of 5.5, and I think I better do these on a calculator. Actually, I made a mistake here. You want to take the second number minus the first number. So this difference is negative, this difference is negative, and now I want 2.75 minus 5.5. That's going to be a difference of negative 2.75. And here, 1.375 minus 2.75 is negative 1.375. Now I look at my next row of differences. And we need to be careful here. Negative 5.5 minus negative 11. That's going to be positive 5.5. And now do the next two on a calculator. Notice that these differences happen to be positive. Now looking at the third row, 2.75 minus 5.5 is negative 2.75. And 1.375 minus 2.75 is negative 1.375. So I am not getting constant differences. So it's back to the drawing boards. So I'm going to erase this. In our secret, if the differences do not turn out to be constant, it's probably not a polynomial. So we go to step 2, which is looking at the quotients of successive terms. So now we're going to take the second term divided by the first term. The second term divided by the first term is 1/2. This is what I'm multiplying by. This is the common ratio. 1/2, 1/2, 1/2. I hope you see the similarity to what we did back with geometric functions. So answer A here is geometric or exponential. So back up here at the 0 point, I'm multiplying by 1/2. These are the multipliers. Multipliers. And so the reverse process of multiplying by 1/2 is multiplying by 2, which means this needs to be 44. So my formula here is y equals 44 times 1/2 to the x power, or NaN is equal to 44. If you can write 1/2 as 0.5 if you want also. Either of these answers is correct, and it's important to realize that they're giving us the same sequence. Finally, my last example is going to turn out to be cubic. So let's write this out and get the rows of differences, and the third row of differences is going to be constant. I'm going to let you make the table ahead of me. Here's my first column or first row of differences. It's not constant, it's not linear. Now when I do my second row, I'm getting 12, 18, 24, and 30. That's not constant, therefore it's not quadratic. If I do the next row, I get a constant difference of 6. When the third column of differences is constant, it's going to be cubic. Doing this by hand would be quite a bit of work because I have 4 coefficients, A, B, C, and D to worry about. So I'm going to allow you to use Desmos. Let's see how this is done in Desmos. Earlier in the video, I showed you how to start with a formula and get a table. This time, I'm going to start with a table and we're going to recover the formula. So I'm going to create a table and I'm going to put in our values here. I think it went up to 6. And I'm going to put in my y values. 4, 7, 22, 55, 112, 199. And now I'm going to get the approximation. And this is going to be a perfect fit. By the way, if you forget how to do this and you don't want to watch my video again, I believe right here under Help, right here, it explains how to do regressions. And it's going to take you through the process here. I think I do remember how to do it, so I'm going to show you how to do it. We use Y1 because this is Y1 here, and it's going to use the 6-element list. Instead of equals, I use the tilde, which means it's going to be approximately equal. Now, the power and beauty of Desmos is you can put in any format that you want. I want A times x1 to the third power plus B times x1 squared plus C times x1. You do have to put the 1. If you don't put the 1, I don't think it'll work. Plus D, and hit enter. Now, if you've done regressions before, here's r squared. When you have r squared equals 1, that means it's a perfect fit. And we can see here that this goes through the points exactly. I'm going to change my window here a little bit. That's under the wrench. X only needs to go from about -3 to 10 or so. But Y needs to go all the way up over 199, maybe 250. So we can see here that I have a perfect fit for my cubic. And my coefficients are 1. Okay, now this is interesting here. And I've got a little bit of a bug here. I've got a little bit of a bug here on my display. This is times 10 to a negative power. And I'm not sure if I can get that to show up properly. C is -4 and D is 7. Okay, and this is a little bug in Desmos, and I'll probably tweet this out to Desmos, and I'll bet you I'll have it fixed in a week. If I take this out of projector mode, we can see here that B is 1.16 times 10 to the -14th, which is a tiny, tiny number. The algorithm has stopped at a certain point. Basically, this means B is 0. If I put it in projector mode, I'm not seeing the negative exponent. So that's a little bug in Desmos, which is actually fairly common with technology. You've got to make sense of it. So let's go back to our handout and write down the answer. This is a cubic relationship. And my formula is y equals 1 x cubed plus 0x squared, I'm not going to write that in, minus 4x plus 7. And you can check this with Desmos or check it with a graphing calculator. Using the sequence notation, an is equal to n cubed minus 4n plus 7. One of the challenges here is the notation. Notation is always a challenge, so please call me or ask questions either online or in the Zoom exchange to help clarify and make sense out of the notation. This has been a video on finding formulas for sequences. Now let's go over and try some practice problems in the online course. Have a great day.